Okay, we have another quiz video. We're going to start with the information that you've been provided. We're going to be analyzing the inside of a parallel plate capacitor now. We're going to be releasing a charge in the middle of it. So let's make sure that everybody's clear about what this looks like before you begin. When you read this kind of problem on an exam, you should be reading this as we have a set plate separation distance of 2 millimeters, and we have a voltage across the plates of 25 volts, and we're going to be releasing a proton exactly in the middle, so that's 1 millimeter from the plate on the left and 1 millimeter from the plate on the right. So you're being asked to determine which direction it's going to go, and also with what speed will it strike the plate. So give it a shot. Come back if your answer is different than mine. Okay, so let's start off with, let's choose sides here. We're going to make this side positive and this side negative. And when we release our proton, our first question is pretty quick to answer. That is, we're releasing a positive charge in here, so very easily you can see the electric field inside here is pointed to the right. And since this is a positive charge, because it's a proton, it should be going along the field line. Also, without drawing your electric field, it should be obvious that a proton would be repelled from positive charge and attracted to negative charge. So, toward the negative plate. That one should be a pretty straightforward and simple answer. The next part we'll have to think about a little bit more carefully and do some math. In part B, we're asked with what speed it will strike the plate. This should hit you as a conservation of energy problem. So whenever you have conservation of energy problems, you're always going to want to look at the initial potential energy plus the initial kinetic energy should be equal to the final potential energy plus the final kinetic energy. That should be old hat from Physics 1, so let's go ahead and figure out which ones of these that we can eliminate to make things easier on ourselves. Originally, when we release this, we're releasing it, and therefore it's starting from rest, which means that we can go ahead and eliminate the initial kinetic energy because we know that it's not moving in the beginning, right? Now, as for whether we can eliminate something else, that depends on how we set this up. If we set this up to be that this is the 0-volt plate, which is pretty standard for us to do with parallel plates, the positive plate is then selected as the positive 25-volt plate. And that means that if we know our potential at this point is 0 volts, then when the proton arrives there, that's going to be also the potential energy is going to be 0. So let's select this as 0.1, and we'll select this as 0.2, right? And if you wanted to change your subscripts, you could change it to be that the potential energy at 0.1, kinetic energy at 0.1, potential energy at 0.2, and kinetic energy at 0.2, if that's easier on you. So, because we know that when we reach 0.2, the potential energy is going to have been depleted because we've reached the 0 point. Because we have potential energy everywhere uphill from 0, but we've defined this to be the 0 potential energy position. Conveniently, that eliminates this from our equation. So, this is looking easier and easier. We can see that the initial potential energy is equal to the final kinetic energy. Now all we have to do is figure out what each of these is. So the initial potential energy should be given by an electrical potential energy equation, which is valid for the parallel plate capacitor. This is always going to be valid, right? If you're looking at this as this, then you're completely approaching it in a way that is not valid. So I see this a lot. You do not want to use this equation in this case because this is a spherically symmetrical charge distribution and is not valid in the case that we are in right now. As a matter of fact, this is so much easier than that. You don't even need to go through that whole process. We know that every point along this inside of the parallel plate, along the separation distance, is going to be scaling linearly with the voltage, right? So the middle point here should be half the voltage between 25 and 0. So we know that the voltage at point 1 is going to be 12.5 volts because that's exactly half of 25 volts. We also know that the voltage at point 2 is going to be 0 volts, right? Well, and that's actually what we use to eliminate this. Okay, so we really don't actually need that, but that's just for clarity. So this means then that our potential energy at point 1, which is, we also labeled this as our initial potential energy, is going to be QV. So that's the charge of a proton. It's positive, not negative, right? Times our voltage, which is 12.5 volts, right? And that gives us 2.0 times 10 to the negative 18 joules of energy. And that's what we start with. Now, you know kinetic energy. Kinetic energy is always going to be equal to 1/2 mv squared. So this allows us to calculate for our velocity. So in this case, remember, you can multiply both sides by 2 to get rid of the half, and then divide by both sides to get rid of the m on this side, and that should give you v squared is then 2 over the mass times, and then also remember, if you take the square root of both sides, then you get the speed of the thing, okay? Our mass of a proton is, you can look the information up in your book, 1.67 times 10 to the negative 27 kilograms, and it should also be on your equation sheet. So that gives us then, if we fill that in for m here, that gives us 48,900 meters per second. That is 49 kilometers per second, which is incredibly fast. But it makes sense because it's a light object, right? So for part B, we get the speed is 48.9 kilometers per second. Okay, I'm going to clean this up. Okay, if that's the answer you got, you're gold, but if not, then go back and watch the video to see how we got there.